Hey everyone, and welcome to today's Explainer. Today, we are absolutely unpacking a fascinating mystery of space, the mechanics behind geostationary satellites. I mean, we literally rely on them every single day for global communication, live TV, you name it. But the physics actually keeping them up there, it's nothing short of mind-bending. Let's get right into it.
So think about this paradox for a second. How exactly can an object, we're talking about a massive piece of metal flying through space, travel at unbelievable speeds of thousands of meters every single second, yet appear completely motionless from our perspective down here on Earth? It really sounds physically impossible at first glance. But as you'll see by the end of this explainer, it's actually an incredible trick of physics.
Here is our roadmap for today. We're going to cover the illusion of stillness, the strict conditions for orbit, how we calculate the height, determining the orbital speed, the real reason they need such high altitude, and wrap up with geostationary versus polar orbits.
Okay, Section 1, the illusion of stillness.
To really grasp this illusion, we have to remember a fundamental rule of physics: rest and motion are completely relative. The word itself kind of gives the whole game away, right? Geo stands for Earth, and stationary means at rest. Basically, a geostationary satellite has a revolving time period that perfectly, and I mean perfectly, matches the Earth's 24-hour rotation. As the Earth spins around its axis once every 24 hours, the satellite is completing one full revolution in its orbit in that exact same 24-hour window. Because their timing is flawlessly synced up, if you look up from a fixed point on the ground, the satellite just hovers there. It never seems to move across the sky.
Picture it this way. Imagine two cars driving side by side down a highway, and both are cruising at exactly 20 kilometers per hour. If you're sitting in one car and glancing over at the driver of the other, they aren't moving forward or backward relative to you, right? To you, that other car is completely stationary. But of course, an observer standing on the sidewalk sees both of you flying by. That exact same concept of relative motion is what's happening between our satellite and the spinning Earth.
Moving on to Section 2, the conditions for orbit.
You know, you can't just toss a satellite randomly into space and expect it to magically behave this way. To hit this geostationary sweet spot, a satellite has to meet 4 non-negotiable rules. First, the orbit must be perfectly circular. Second, it has to be placed directly above the Earth's equator. Third, it needs to rotate from west to east, matching the Earth's own rotation. And fourth, it must maintain exactly a 24-hour time period. If even one of those variables is just slightly off, the entire illusion breaks down and the satellite starts drifting across our sky.
All right, Section 3, calculating the height.
So where exactly is this sweet spot? Let's figure out the precise distance out in space where all those rigid conditions are actually met. Now, any object moving in a circle requires a centripetal force constantly pulling it inward, kind of like an invisible tether. For our satellite, Earth's gravitational pull acts as that essential tether. By equating the centripetal force directly with gravitational force, we can isolate the velocity. That gives us our very first crucial formula. Velocity equals the square root of the gravitational constant times the mass of the Earth divided by the orbital radius.
But wait, we actually have another, much simpler way to think about velocity. It's really just distance over time. For a circular orbit, that distance is simply the circumference of the circle, which is 2 pi r, and the time is our trusty 24-hour period, which we'll call t. So our second formula is just v equals 2 pi r divided by t. Let's see what happens when we mash this together with our previous formula. Now for a bit of mathematical magic. To find the height, our goal is to isolate the radius, r. We start by squaring both sides just to get rid of that pesky square root, and then we group all our variables together on one side. Once we take the cube root, we arrive at a beautiful, elegant piece of physics known as Kepler's relation. Think about it. We know gravity, we know the Earth's mass, and we know our time is exactly 86,400 seconds, because that's 24 hours converted into seconds.
When we plug all those massive, intimidating numbers into a calculator, we get a surprisingly satisfying and precise result: 43,200 kilometers. But hold on, r actually represents the distance from the very center of the Earth all the way up to the satellite.
And obviously, we don't launch satellites from the Earth's fiery core, right? We launch them from the surface. Since the Earth's radius is roughly 6,400 kilometers, we just subtract that from our total. 43,200 minus 6,400 gives us exactly 36,800 kilometers. And there it is. That is the exact mandatory altitude above the Earth's surface where a geostationary satellite has to be parked.
Section 4, determining the orbital speed.
Okay, so we know exactly where it needs to live. But just how fast is this completely stationary object moving through the void of space to maintain that perfect orbit?
To figure this out, we just loop back to our very first mathematical step. Remember that formula we built? V equals the square root of gm over r? Well, earlier we were kind of stuck because we didn't know what r was. But now we do. So we can just plug in our newly calculated orbital radius along with the gravitational constant and the mass of the Earth.
Crunch those numbers, and you get a final orbital velocity of 3.07 kilometers per second. I mean, let that sink in for a second. To stay perfectly still relative to your house, this satellite is screaming through space at over 3,000 meters every single second. Which brings us to Section 5, the high-altitude reason.
You might be wondering, why go through the immense trouble and crazy cost of sending these machines 36,800 kilometers away? Why not just park them closer? The secret is in a fascinating inverse relationship. The closer an object is to Earth, the stronger the Earth's gravitational pull is. So to avoid literally falling out of the sky, a low-orbit satellite has to travel incredibly fast. But a larger orbital radius, being much further away, means gravity is slightly weaker, which allows for a slower necessary orbital velocity.
Let's put that into perspective. If we put a satellite in a low orbit, it has to move so blindly fast to fight gravity that it finishes a lap in way less than 24 hours. It would just zip right past us. By pushing it way out to that extreme high orbit of 36,800 kilometers, the satellite is forced to slow down to that specific 3.07 kilometers per second speed. And that exact slower speed is what stretches the lap time to a perfect 24 hours, beautifully syncing with the Earth's spin.
Finally, Section 6, geostationary versus polar orbits.
Contrasting our geostationary satellite with another famous type of orbit really cements how unique this whole setup is. While geostationary satellites orbit way out around the equator, polar satellites orbit top to bottom, right over the poles. Because polar satellites are much closer to Earth, they complete multiple rapid laps a day, making them absolutely amazing for mapping and surveillance. Geostationary satellites, on the other hand, stay locked over one single area, making them the total backbone of our live broadcasting and global telecommunications.
To wrap up today's explainer, I want to leave you with a bit of a provocative thought experiment. Imagine one of these geostationary satellites is accidentally nudged by a micrometeor into a slightly lower orbit. Based on that inverse relationship we just talked about, what would happen to its velocity? Because it's closer to Earth, would it have to speed up to fight gravity? And if it speeds up, does it suddenly fall behind the Earth's spin or race ahead of it? Think about it. Thank you so much for joining me today for this explainer. Keep exploring, and I'll catch you next time.